I want you to imagine that you are sitting alone at a dinner table late at night, and in front of you are two identical glasses, same shape, same weight, same clear surface catching the light. You reach for the first glass, and your hand closes around it exactly as you expect. Then you reach for the second. Your fingers pass through empty air, and the glass is still there. You can see the effect it has on the table. You can see the shadow it seems to cast and the arrangement of everything around it. You can infer its presence from what the room is doing, but you cannot touch it. You cannot taste what is inside it. You cannot interact with it in any ordinary way. Now, enlarge that image until the table becomes the universe. Everything you have ever seen, every star, every planet, every atom in your body belongs to one glass. And the other glass, it may contain an entire hidden sector of reality, particles we have never detected, forces that do not act on ordinary matter, perhaps dark atoms, perhaps dark radiation, perhaps a parallel family of particles organized by laws that resemble our own. I need to tell you immediately what this does not mean. Physicists have not discovered another Earth occupying the same room as ours. No telescope has photographed a mirror galaxy made of mirror people. There is no confirmed evidence that a complete duplicate universe exists beside us. But modern particle physics has left open a startling possibility. The matter we know may be only one sector of a larger theory, and the invisible matter whose gravity shapes galaxies may not be a single missing particle at all. It could be complicated, it could have structure, it could possess its own interactions. In some models, it could even resemble a hidden copy of the particle world we already know, and that is the door. And if nature has built a second sector beside ours, then most of reality may be happening in a language our ordinary senses cannot read. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to explore the places where established physics ends and the hidden architecture begins, you're in the exact right place. Now I want you to imagine an old theater. You are sitting in the audience. The stage is brightly lit. Actors move across it. You can see every costume, every face, every prop. Behind the stage is a heavy black curtain. There is something behind it because the actors occasionally disappear through openings in the fabric. The floor vibrates, ropes move, lights change. But from your seat, everything behind the curtain is invisible. Hold on to that image. The standard model of particle physics is our illuminated stage. It describes the known elementary particles with extraordinary precision. There are quarks, which combine to form protons and neutrons. There are leptons, including electrons and neutrinos. There are force carrying particles, photons for electromagnetism, gluons for the strong nuclear force, and the W and Z bosons for the weak force. And there's the Higgs field, associated with the Higgs boson discovered at CERN in 2012, whose interactions help give elementary particles their masses. This theory works so well that some of its predictions agree with experiments to astonishing precision. And yet, the standard model is obviously incomplete. It does not explain dark matter. It does not naturally incorporate gravity as a quantum interaction. It does not explain why there is far more matter than antimatter in the observable universe. It does not explain the full pattern of particle masses. And depending on how deeply you ask the question, it leaves us wondering why the Higgs mass is as small as it is compared with vastly higher energy scales. And the stage is magnificent, but the curtain is still moving. The clearest evidence that something lies beyond the standard model comes not from a particle collider, but from the sky. Galaxies rotate too quickly for their visible matter alone to hold them together. Galaxy clusters contain far more gravitating mass than we can account for with stars and hot gas. Light from distant objects bends around invisible mass through gravitational lensing. The cosmic microwave background carries a pattern that strongly indicates the presence of non-baryonic matter. The large-scale cosmic web grows as though most matter is invisible, and we call this missing component dark matter. The name sounds more informative than it really is. Dark matter is not a substance we have placed in a bottle It is a label for gravitational behavior that demands an explanation. For decades, many physicists hoped the answer would be elegant. One new particle, perhaps a weakly interacting massive particle, a WIMP, a single addition to the inventory, one invisible brick, but direct searches have become extraordinarily sensitive. And so far, no universally accepted dark matter particle has appeared. And this does not mean WIMPs are impossible. It means the search has broadened. Axions, ultraviolet fields, sterile neutrinos, primordial black holes, composite dark matter, and something more radical, a dark sector. I want you to imagine opening a toolbox. At first, you believe one tool is missing. You count the hammer, the wrench, the screwdriver, the pliers. There is one empty slot. So you search for the missing tool. Years pass, nothing fits. And then someone notices that the bottom of the toolbox lifts upward. Underneath is another entire tray. That is the conceptual shift from dark matter as one particle to dark matter as a sector. A sector means there may be multiple particles. There may be a dark force. There may be dark versions of radiation. There may be particles that bind together. There may be states that decay into one another. The dark matter we infer gravitationally might be the simplest visible consequence of a much richer hidden system. A name is just a label for our own ignorance. And dark matter may be one of the largest labels we have ever written. Here's the hard truth. We know from gravity that something is there. We do not know how simple it is. And that uncertainty is enormous. Ordinary matter is not simple. Imagine an alien astronomer who could detect only the gravitational influence of Earth. From gravity alone, would it infer oceans? Chemistry, proteins, cities, music, it might conclude that Earth is one approximately spherical mass. That conclusion would be gravitationally useful and almost completely blind to complexity. Why should we assume the dark universe is simpler than ours? Perhaps it is, but simplicity is an assumption, not an observation. Now I want you to return to the theater. Suppose there is not merely machinery behind the curtain. Suppose there is a second stage. On our stage, particles interact through familiar forces. On the hidden stage, another set of particles interacts among itself. The two stages may communicate only weakly, perhaps through gravity, perhaps through rare quantum portals connecting the sectors. This is the basic intuition behind many hidden sector models, and some versions take the symmetry even further. They propose a mirror sector, and imagine placing a perfect mirror down the center of the particle world. On one side are the particles we know, on the other is another family related to them by symmetry, a mirror electron, mirror quarks, mirror photons, mirror versions of interactions. Different models implement this idea differently, and modern twin sector theories are not all literal copies of our world. But the central thought is profound. Nature may possess more symmetry than the matter visible to us reveals. Part of the particle spectrum may be hidden because it interacts only feebly with our sector. If so, the universe could contain an enormous amount of physical activity that does not produce ordinary light. You could be immersed in it now, not in the science fiction sense of another person standing invisibly beside you, in a particle physics sense that hidden particles could pass through or surround ordinary matter while scarcely interacting with it. This brings us to the first major question. Why would physicists invent something so extravagant? One answer comes from the Higgs boson. The Higgs is unusually sensitive to quantum corrections. If there is new physics at extremely high energy scales, calculations tend to push the Higgs mass upward unless some mechanism protects it. And this is related to what physicists call the hierarchy or naturalness problem. One family of theories, known as twin Higgs models, introduces a partner sector. The symmetry between our sector and the twin sector can help stabilize the Higgs mass against large quantum corrections. In other words, the hidden world is not added merely because it sounds mysterious. It can emerge as an attempted solution to a concrete problem in particle physics. hold on to the mirror. In the simplest conceptual picture, the visible and twin sectors are related. But the symmetry does not require us to live beside an exact duplicate civilization. Um, and the thermal histories can differ. The particle masses can differ in some variants. The abundance of matter can differ. The hidden sector can evolve under conditions dramatically unlike ours. The word mirror describes a mathematical relationship, not necessarily a cosmic photocopy. This distinction is essential. When a popular headline says second reality, the defensible scientific version is not another universe identical to ours has been found. It is this: the fundamental theory may contain degrees of freedom that are largely invisible to standard model particles, yet physically real. That is already extraordinary enough. And in June 2026, research published in Physical Review D continued exploring exactly this territory. One model studied a hadrosymmetric dark matter sector related to mirror twin Higgs ideas, examining whether a duplicated or partially duplicated particle sector could help address cosmological tensions while supplying dark matter. That is not proof, it is active theory building. But the fact that these models survived long enough to be confronted with cosmology tells you something important. The hidden sector idea is not restricted to science fiction. It lives inside equations that must face real data, and this is where the coin becomes rigged. Imagine flipping a coin 1,000 times. You expect roughly half heads and half tails. Instead, you obtain a subtle excess, not enough to declare that probability has failed, enough to make you inspect the coin. Particle physicists search for hidden sectors through tiny deviations from ordinary expectations. Perhaps a known particle decays into invisible products. Perhaps an event inside a collider appears to lose energy and momentum. Perhaps a long lived particle travels some distance before decaying unexpectedly. Perhaps a new force carrier, called a dark photon, mixes faintly with the ordinary photon. Perhaps the Higgs itself acts as a portal. The visible stage may occasionally leak information from behind the curtain. The coin is rigged, or at least that is what we are trying to determine. CERN is now taking these possibilities seriously enough to build experiments specifically aimed at feebly interacting particles. The SHIP experiment is designed to search for particles that interact so weakly with ordinary matter that conventional collider detectors may miss them. This is a remarkable change in experimental philosophy. The Large Hadron Collider was designed in part to explore high energies directly. Hidden sector searches often require a different strategy, not merely smashing harder, listening longer, looking farther downstream, searching for particles that survive because they barely notice our world. Imagine shouting into a cave. You expect an echo immediately. Nothing returns. So instead of shouting louder, you place a microphone deep inside the mountain and wait for the faintest vibration. So that is the hidden sector problem. The interaction may be so weak that absence of detection is exactly what the theory predicts most of the time. This makes experimental design difficult. It also makes every potential portal precious. One possible portal is kinetic mixing. An ordinary photon is the quantum of our electromagnetic field. A dark sector could contain a dark photon associated with a hidden electromagnetic like force. Under certain theories, the ordinary photon and dark photon can mix extremely weakly. This could allow hidden particles to communicate faintly with charged ordinary particles. Another possibility is the Higgs portal. Because the Higgs field is a fundamental scalar field permeating space, it may couple to hidden scalar particles. A third class involves neutrino portals, where new neutral fermions communicate through interactions involving known neutrinos. These portals are like tiny cracks in the wall between rooms. The rooms do not need to share a door. A whisper can still pass through. Now I want you to really grasp what this means. If hidden particles have their own forces, then dark matter may collide with itself. It may radiate dark photons. It may cool. It may bind. And in some models, there could be dark atoms. The analogy is dangerous if taken too literally, but useful if handled carefully. Ordinary atoms exist because electrically charged electrons and nuclei interact through electromagnetism. If a hidden sector contains particles carrying opposite charges under a dark electromagnetic force, analogous bound states can form mathematically. Dark chemistry becomes conceivable, not chemistry involving our photons, not molecules we can smell or touch, a hidden network of bound states governed by a hidden force. The moment you permit this, the phrase dark matter becomes almost comically inadequate. It is like calling biology wet carbon, technically suggestive, conceptually impoverished. Could a dark sector form dark stars? In some dissipated models, hidden matter could lose energy and collapse into compact structures. Could it form dark disks inside galaxies? Under certain interactions and abundance assumptions, researchers have explored such possibilities. Could there be dark acoustic oscillations analogous in some respects to phenomena in the visible plasma of the early universe? Yes, some dark sector cosmologies predict them. Every one of these possibilities must survive observational constraints, and those constraints are severe. The cosmic microwave background is an unforgiving witness. Big Bang nucleosynthesis constrains extra radiation in the early universe. Galaxy structure constrains how strongly dark matter can interact. Cluster collisions constrain self interactions. Gravitational lensing maps the distribution of mass. The success of large scale structure restricts how dark components can behave. A hidden world cannot simply do anything it wants, it must remain hidden while still producing the universe we observe. That is an extraordinarily narrow balancing act. This is where human intuition entirely breaks down. We hear hidden universe and imagine a second transparent sheet laid on top of ours. But quantum field theory does not organize reality according to what human eyes consider separate. Different fields can occupy the same space time. Right now, the room around you is filled with electromagnetic fields. Neutrinos pass through Earth. The Higgs field is present. Gravitational fields extend through everything. If dark fields exist, they do not need another geometric location. They can be here while remaining dynamically separated. The second reality may not be somewhere else. It may be the part of here that we cannot couple to. Think about the space between your hands. It feels empty, but in modern physics, empty space is not nothing. Quantum fields exist throughout it. Particles are excitations of those fields. If another set of fields also permeates space, your senses would have no obligation to detect them. Human perception is a tiny biological filter. Your eyes respond to a narrow range of electromagnetic wavelengths. Your ears respond to pressure oscillations in matter. Your skin responds to certain mechanical and thermal interactions. Reality was not designed to fit through those channels. We built particle detectors precisely because nature exceeds our senses, and hidden sectors push that lesson to its extreme. There may be fields that scarcely interact even with our instruments. How then could we ever know they exist? Gravity, the universal accountant. Gravity responds to energy and momentum regardless of whether matter glows. This is why dark matter was noticed at all. Its gravitational influence bends trajectories, shapes galaxies, and curves spacetime. A sufficiently complex hidden sector could therefore announce its existence through structure rather than light. The universe becomes a shadow play. You never see the actor. You see the curtain move, but gravity alone may not tell us whether the dark sector contains one particle or 100. For that, we need fingerprints. Self interacting dark matter offers one example. In the simplest cold dark matter picture, dark particles interact primarily through gravity and rarely collide with one another. But if hidden forces exist, dark matter could scatter off itself. Galaxy clusters provide laboratories for testing this. When clusters collide, ordinary hot gas experiences electromagnetic drag and shocks. Galaxies mostly pass through. Dark matter's distribution can be mapped through gravitational lensing. If dark matter strongly collided with itself, its mass distribution could lag or deform in characteristic ways. Observations have therefore placed constraints on dark matter self interaction. Those constraints do not eliminate all hidden sector models. They tell model builders how dark the hidden interactions must remain. Think of an invisible ocean. We cannot see the water, but we can watch ships move through it. If the ships slow down, we infer viscosity. If they pass freely, we infer something else. Cosmic collisions let us estimate properties of a substance we cannot directly capture. This is one reason I resist the phrase, we know nothing about dark matter. We know a great deal about what dark matter must do gravitationally. We know many things it cannot do too strongly. And what we do not know is its identity. That is different. And identity is exactly where the second reality becomes possible. Now, I want you to imagine a cello. One string is visible, the other is behind the instrument, hidden from your eyes. You pluck the visible string, it vibrates. Under the right conditions, the hidden string begins to resonate faintly because the two are coupled through the wooden body. You cannot see the second string, but its resonance modifies the sound. This is how physicists think about portals. Our particles are the visible string, the hidden sector is the unseen string. A tiny coupling allows one side to influence the other. The task is to find the change note. At the Large Hadron Collider, this can mean missing transverse momentum. Collisions begin with known conditions in the plane transverse to the beams. If invisible particles carry momentum away, the visible products fail to balance. But missing momentum is not automatically dark matter. Neutrinos already do this. Detector imperfections can mimic it. Background processes can imitate exotic signals. Again, the coin must remain rigged after every ordinary explanation is removed. Other experiments search for displaced vertices. A hidden particle may be produced and travel an unusual distance before decaying back into visible particles. Instead of a decay occurring at the collision point, tracks suddenly appear centimeters or meters away. That geometric separation can become a signature of a long-lived particle. Dedicated experiments extend the search even farther. And the philosophy is beautiful. If the hidden world barely talks to us, build a detector optimized for whispers. Here is the hard truth. So far, no experiment has established the existence of a complete hidden sector. No dark photon has been universally confirmed. No twin particle has been identified. No mirror atom has been captured. The entire framework remains hypothetical, and yet it survives because it connects multiple unsolved problems while producing testable consequences. That is what separates serious speculation from fantasy. A theory must risk death, and it must tell us what we could observe that would rule it out. The hidden world has many possible forms, but each form is forced to negotiate with data. The early universe is one of the strictest negotiators. If a mirror sector contains too much radiation, it changes the expansion rate during Big Bang nucleosynthesis. That changes the predicted abundances of light elements. And if it interacts too strongly, it alters the cosmic microwave background. If it clusters incorrectly, it changes galaxy formation. If hidden acoustic effects are too large, they modify the matter power spectrum. If dark atoms cool too efficiently, they could form structures inconsistent with observations. Cosmology is therefore not merely looking for the hidden sector, and it is squeezing it, reducing the space of possibilities, forcing the invisible world into a smaller and smaller room. And occasionally, theoretical ideas become interesting because they may address more than one tension at once. Some recent mirror and twin sector work explores whether the hidden sector could influence quantities related to early universe radiation and the inferred expansion history while also supplying dark matter. And again, this is not a solution accepted by consensus. It is an active attempt, but notice the structure of the problem. The visible universe gives us several puzzles: the Higgs mass, dark matter, cosmological tensions. Perhaps these are unrelated, or perhaps they are shadows cast by one hidden architecture. Physics has seen this before. Electricity and magnetism appeared to be separate phenomena until Maxwell unified them. Space and time appeared separate until relativity combined them into space time. Different particles were organized by deeper symmetries in the standard model. Nature sometimes presents multiple puzzles whose solutions turn out to be one idea viewed from different directions. That possibility is why the hidden sector is so seductive and so dangerous. Seductive theories invite confirmation bias. The more problems a framework might solve, the easier it is to begin seeing evidence everywhere. So we must return to the discipline of measurement. What would convince us a reproducible laboratory signal consistent with a new feebly interacting particle, a characteristic invisible decay of a known particle, a dark photon signal appearing across independent experiments, a long lived particle with couplings fitting hidden sector predictions, a coherent astrophysical signature of dark self interactions that cannot be reproduced by ordinary baryonic physics, a cosmological pattern matching a specific dark sector model better than the standard alternatives, not one unexplained bump, a network, because a real hidden sector would not produce one isolated miracle and it would produce consistency. The same parameters would have to work in particle physics and cosmology. The same coupling that produces a collider signal would affect early universe evolution. The same self interaction that shapes a galaxy would matter in cluster collisions. The same dark radiation would leave traces in the cosmic microwave background. The invisible world would cast multiple shadows, and the shadows would have to line up. Now, I want you to look around the room you are sitting in right now. Everything appears ordinary because your brain is built from ordinary matter. You see walls because photons scatter from electrons. You feel the chair because electromagnetic interactions prevent atoms from passing freely through one another. You hear sound because ordinary matter transmits pressure waves. Every sensory fact you call reality depends on a particular set of interactions. Change the interactions, and reality becomes inaccessible. A dark atom, if such a thing exists, would not be dark because someone painted it black. It would be dark because our photons might not couple to it. A dark star would not appear dim in the ordinary sense. It could be electromagnetically absent. A dark cloud could overlap the room and never block a lamp. This is where the phrase second reality becomes emotionally difficult. We are used to thinking that existence means visibility or touch. Physics says otherwise. Neutrinos exist even though trillions can pass through your body with almost no effect. Gravitational waves existed long before we had instruments capable of measuring them. Black holes existed before we had observational evidence for them. Reality does not wait for biology to approve it. And now, perhaps, our most important missing matter belongs to a family of particles that has been present everywhere while remaining almost perfectly indifferent to us. There is an existential vertigo in that idea. Ordinary matter makes up stars, planets, bodies, books, civilizations, everything we have ever directly touched. And yet, ordinary matter is not the dominant form of matter in the cosmos. Most matter is dark. If that dark matter has internal structure, then the majority of material reality may possess properties we have never experienced. You are made from the minority sector. Think about that. The substance that learned to ask what the universe is made of may be made from the less common kind of matter. The visible universe could be the exception observing the rule, but I want to resist turning this into mysticism. There's no evidence that dark matter is conscious, no evidence of hidden civilizations, no evidence of a duplicate Earth, no scientific basis for claiming that ghosts, spiritual realms, or paranormal experiences are dark sector phenomena. Those ideas add conclusions that the physics does not support. The mystery is already profound without borrowing unsupported claims. What physics permits is narrower and more beautiful. Fields, particles, forces, symmetries, interactions of a hidden material sector constrained by equations and experiments. That is enough to rearrange our concept of the universe. Return to the two glasses on the table. At first, one seemed real and the other impossible. Then gravity taught us that the invisible glass has weight. Galaxy rotation told us it was there. Lensing outlined its shape. The cosmic microwave background told us it existed early. Structure formation showed us how deeply it influenced cosmic history. But we still do not know what is inside it. Perhaps one particle, perhaps a family, perhaps a mirror, perhaps something stranger than any analogy we currently possess. The next generation of experiments will attack the question from many directions. Collider experiments will keep searching for missing energy events and long lived particles. Beam dump and fixed target experiments will hunt feeble interactions. Axion searches will explore ultralight possibilities. Direct detection experiments will push sensitivity to new masses and couplings. Astrophysical surveys will map dark matter through gravitational lensing. Cosmic microwave background measurements will tighten constraints on hidden radiation and interactions. Gravitational wave observations may eventually probe dark compact objects or phase transitions in hidden sectors. Each experiment illuminates a different corner behind the curtain. Maybe they will reveal nothing. That possibility matters. No results eliminate theories. The hidden room becomes smaller. Perhaps nature chose a single simple particle after all. Perhaps dark matter interacts only gravitationally. Perhaps the twin sector idea solves an aesthetic problem but is not realized in nature. Science must allow those outcomes, but if even one portal opens, the consequences will be enormous. Finding one genuine hidden sector particle would do more than add a line to the particle table. It would prove that the standard model stage is not the entire theater. We would immediately ask what else lives there, what symmetry organizes the sector, what forces act within it. Did the hidden particles exist during the Big Bang? Did they contribute to dark matter? Can they form bound states? Do they alter stars? Do they change the thermal history of the universe? Is the sector minimal or rich? One particle would turn a philosophical possibility into an experimental program. This is how revolutions begin, not with the final theory, with the first undeniable crack. Newton did not finish gravity. Einstein did not finish space-time. The discovery of the electron did not finish particle physics. The Higgs did not finish the standard model. Each answer made the remaining ignorance more precise. If a hidden sector is discovered, the same thing will happen. The universe will become larger without expanding by a single meter. Our definition of reality will expand instead. Now it is our turn. For centuries, humans increased the size of the known world geographically, then astronomically, then microscopically. We discovered continents, planets, galaxies, atoms, nuclei, quarks. Perhaps the next expansion is not farther away or smaller in scale. Perhaps it is orthogonal to everything we can directly see. Another sector occupying the same cosmos, another set of fields, another family of particles, a world hidden not by distance, but by interaction. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless distinction between what the equations permit and what the data has actually established. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long form explorations possible. But before we end, I want to return to the images we carried through this journey. The two glasses taught us that something can have physical influence without being directly touchable. The theater taught us that the standard model may be only the illuminated stage. The hidden tray taught us that dark matter might be a sector rather than a single particle. The mirror taught us that symmetry can duplicate structure without creating a science fiction copy of our world. The cello taught us how weak portals might let one sector whisper into another. And gravity taught us that even a silent world cannot completely hide its weight. We have not discovered a second reality, but modern physics has reached a point where that phrase can be translated into a serious scientific question. Could the universe contain a hidden sector of particles and forces largely invisible to ordinary matter? Yes. Could it be rich enough to resemble, in some mathematical sense, another material world? Some theories say yes. Do we know that nature chose those theories? No, not yet. The door is still closed, but CERN is listening near the hinges. Cosmologists are watching the shadows under the frame. Particle physicists are searching for missing energy escaping through cracks. And if one day the door moves even slightly, we may discover that the greatest hidden territory in the universe was never beyond the edge of the observable cosmos. It was here the entire time, in the space between your hands, sharing our universe, carrying gravity, and waiting for matter like us to finally notice